Hi, my name is Dan Bullard, and I've been teaching electronics for years and years, and I like to help people get through op amps because op amps can be problematic. So I'm going to show you how to figure out an op amp circuit, a particularly difficult circuit in this case, show you how to solve it and get the right answer every time. First thing you need to know is a few rules about op amps. Rule number one is that no current ever flows into or out of the inputs. That is always true. Rule number two is that whatever voltage you have on one input will be on the other input. Now that's not always true, but it's a good place to start. And rule number three is if V out is greater than the supply voltage, then rule number two no longer applies. So that's why rule number two isn't always true. If V out is greater than the supply voltage, rule number two no longer applies. Here we have a fairly complicated looking op amp circuit with a voltage divider for the input and a very strange looking feedback network. The first order of business is to look at the input. So we can see we have 3 volts going to 3 1K resistors. So it looks like a plain voltage divider, but it's hard to tell because we don't know what the current is going from the 3 volt supply through R1, through R2, and then into the op amp circuit with that switch closed. So what could be the current flow and what will be the voltages at those other 2 nodes? But remember, our rules say that no current ever flows into or out of the inputs. So we don't have to worry about any current that might be flowing through R1, R2, and then into R4 into the op amp. There will be no current there, so it won't modify the voltage coming out of our voltage divider network. So now we know we'll have 3 volts on the top tap, 2 volts on the middle tap, and 1 volt at the bottom tap of the switch. So now that we know we have no current flowing through R4, that means no voltage drop, and therefore the voltage off of the voltage divider network coming through the switch, 1 volt, will now appear on the positive input of the op amp. Now remember that op amp rule number 2 said whatever voltage you have on one input will be on the other input. So the negative input of the op amp will now be at 1 volt. And because op amp rule number 1 says no current flows into or out of the inputs, that means there's no current flowing through R5, which means we now know what the voltage is on top of R6. It's 1 volt. And we always go from what we know to what we don't know. Since we know we have 1 volt on top of R6, that means we're going to have 1 milliamp of current flowing through R6 to ground. And since we know the current flowing through R6 to ground is not coming from the op amp, it must be coming from R7. And a current flowing through R7 is going to cause a voltage drop of 1 volt minus on the left plus on the right. And that means that the junction between R7, R8, and R9 is now going to be 1 volt plus 1 volt drop, or 2 volts. And with 2 volts on top of R8, that means we're going to have 2 milliamps flowing through R8 to ground. Now with 1 milliamp going through R7 and then R6 to ground, and 2 milliamps going through R8 to ground, that current must be coming through R9. So that's 1 milliamp plus 2 milliamps, or 3 milliamps going through R9. And if there's 3 milliamps flowing through R9, that means there's going to be a voltage drop of 3 volts minus on the left plus on the right. And now because we know we had 2 volts on top of R8, that means we have a 3 volt drop plus 2 volts, or 5 volts on V out. So V out is now 5 volts. Okay, let's flip the switch and bring in 2 volts and see what happens. 2 volts on the switch coming to R4. Again, no current flowing through R4, so the positive input of the op amp will be 2 volts because, again, no voltage drop, no current, 2 volts on the positive input. 2 volts on the positive input means 2 volts on the minus input according to op amp rule number 2. And there's no current flowing through R5, so we know that the junction between R5, R6, and R7 will also be 2 volts. And with 2 volts on top of R6, and that's a 1K resistor, we know we're going to have 2 milliamps flowing through R6 to ground. And we know that those 2 milliamps are not coming from the op amp through R5, they must be coming from R7, and that's 2 milliamps through a 1K resistor, so that's going to create a voltage drop of 2 volts minus on the left plus on the right. And 2 volts plus 2 volts is 4 volts, so the top of R8 will now be 4 volts. And 4 volts on top of a 1K resistor means we're going to get 4 milliamps flowing through R8. And 2 milliamps plus 4 milliamps is 6 milliamps. And 6 milliamps flowing through a 1K resistor is going to create a 6 volt drop. So 4 volts plus 6 volts means that V out is now 10 volts. Now, assuming this is a rail-to-rail op-amp, the output can be 10 volts. Since the supply voltage is 10 volts, 10 volts is about as high as V out can ever get. And now we can talk about gain. Gain is defined as delta V out over delta V in. Since we had a 5 volt change on the output for a 1 volt change on the input, that means the gain of this circuit is 5. You don't need an advanced math degree to figure that out. Just work out the math using Ohm's law and you've got the answer. Okay, let's flip the switch one last time and take it to 3 volts. So 3 volts going to the positive input of the op-amp, because again there's no current flow through R4, so no voltage drop. 3 volts on the positive input of the op-amp. Rule number 2 says the same voltage will be on both inputs, so the minus input of the op-amp will now be at 3 volts. We know there's no current flow through R5, so the top of R6 will now be at 3 volts. 3 volts on top of a 1K resistor connected to ground means 3 milliamps going through R6. That 3 milliamps can't be coming from R5, so it must be coming through R7. And 3 milliamps flowing through R7 means a 3 volt drop, minus on the left, plus on the right. And 3 volts on top of R6 plus the 3 volt drop on R7 means the junction between R7, R8, and R9 is at 3 volts plus 3 volts, or 6 volts. And 6 volts on top of R8 means we'll have 6 milliamps flowing through R8. Now we know we had 3 milliamps flowing through R7 and 6 milliamps flowing through R8 to ground, so 3 milliamps plus 6 milliamps is 9 milliamps. So 9 milliamps is flowing through R9. 9 milliamps through R9 means we'll have a 9 volt drop across R9, minus on the left, plus on the right. And the voltage at the top of R8 was 6 volts, so 6 volts plus that 9 volt drop means we had 15 volts on V out. But wait a minute, we can't have 15 volts out there because the supply voltage is only 10 volts. So again, assuming this is a rail-to-rail op-amp, the output will not be 15 volts, it'll go to 10 volts, the positive supply voltage, and now we get to go backwards and figure out the whole circuit in reverse. The first step is coming up with the equivalent circuit. So we develop an equivalent circuit, remembering that R5 and the op-amp minus input is not part of the circuit. It is infinity as far as the rest of the circuit is concerned. So R5 and the op-amp minus input don't figure into the equation at all. We calculate the equivalent resistance and come up with a value of 1.66 k ohms, which means 6 milliamps of current flowing into R9. So 6 milliamps flowing into R9 means a 6 volt drop across R9, plus on the right, minus on the left, so 10 volts minus 6 volts is 4 volts. So the top of R8 is 4 volts. 4 volts on top of a 1K resistor means 4 milliamps going through R8. We had 6 milliamps coming in, so the remainder, 2 milliamps, must be flowing through R7. And since we know there's no current flowing through R5 into the op-amp, we know that 2 milliamps is flowing through R6. 2 milliamps flowing through R7 creates a 2 volt drop. 4 volts on one side means 2 volts on the other side. So we have 2 volts on top of R6. That'll cause 2 milliamps to flow through R6 to ground. Our numbers jive, everything's right, no current is flowing into the op-amp. And since no current is flowing into the op-amp, the 2 volts on top of R6 can also now be seen on the top of R5. So the minus input of the op-amp is at 2 volts. And here's where rule number 2 breaks. We have 3 volts on the positive input and only 2 volts on the negative input. The op-amp is in saturation. It's gone as high as it can, 10 volts. It couldn't go to 15 volts. It would if it could, but it can't, so it put out 10 volts, and we end up with 2 volts on the minus input. So that's the meaning of rule number 3. Rule number 3 says if you calculate V out and it comes up to be greater than the supply voltage, then rule number 2 can no longer be trusted. So you have to work the whole circuit in reverse and figure out what the actual voltage will be on the inputs. So the next time you deal with a complicated op-amp problem, remember my 3 rules. No current ever flows into or out of the inputs. The 2 inputs will always be the same voltage unless you calculate a V out that is greater than the supply voltages. Deal with Ohm's law, Kirchhoff's law, and you'll be fine. This is Dan Bullard. Thanks for watching.